most of what we go over today is going to hopefully be familiar. Okay, hopefully going to be a review of the stuff you did in Science 9, where you learned how to name simple binary, ionic, and molecular compounds. We're going to build a little bit on that, okay, and we're also going to learn how to name ionic compounds that have multivalent metals or polyatomic ions in them. That will likely be new for everyone, but it's not a whole lot different than what you already know. Okay, so key points. Identify a compound as ionic or molecular. What does an ionic compound have in it?
A metal and a non-metal.
A metal and a non-metal. Okay, so something from the left-hand side of the staircase and something from the right-hand side of the staircase. Okay, that would be an ionic compound. And a molecular compound would have two non-metals. Okay, so two things from the right-hand side of the staircase. All right, that's how we tell the difference. If it has a metal in it, it's going to be an ionic compound. If it doesn't, it's going to be molecular. And there are different kinds of molecular compounds. There are organic compounds that contain carbon and hydrogen and nitrogen and oxygen, okay, things like that as well. We don't really go into those, you learn about them in Chem 20. So, we've got to learn today to write formulae, that's plural for formula, this formulas is not a thing, okay, and the proper names for simple ionic compounds and molecular compounds. Okay, so as we just said, ionic compounds occur when a metal from the left side of the table and a non-metal from the right react to form a new molecule. Okay? When ionic compounds form, the bond between the metal and the non-metal is actually quite weak. Okay? It involves a trading of electrons. This is actually the process that led Bohr to his planetary model of electron alignment. Okay? He noticed that when ionic compounds were formed, the charges of the two elements changed. Normally, an element, when it's on its own, has no charge. It has the same number of protons and the same number of electrons. When it enters an ionic bond, it actually transfers an electron. Okay? It either loses it or gains it. Okay? And so he noticed that particles became charged after they were involved in an ionic compound. Right? So what he thought was going on, and what we still believe to an extent is going on, is our metal, let's say we'll just use sodium. Okay, according to Bohr, sodium looked like this. And sodium has 11 electrons. So the first ring had 2 in it. Okay, the next ring had 8 in it. And then the last ring had 1 in it. Okay. Bohr knew or had studied and understood that all elements are trying to move towards having their outer shell of electrons be filled. Okay? So that they could be like their nearest noble gas. That would be the elements in group 18 at the far right hand side of the periodic table. Okay? So they want to have their electron alignment look like their nearest noble gas. For sodium to do that, to fill its outer shell, would it be easier for it to pick up 7 more electrons to fill it, or to find a home for 1? What do you think?
To find a home for 1.
Find a home for 1. It's way easier to donate 1 than it is to pick up 7 more. Okay? Now, chlorine happens to be in the opposite situation. So, chlorine's first shell looks just like sodium's. It's got 2 in it. Second shell looks just like sodium. Okay, it's got 8 in it. Its outer shell has 7 in it. How many more does it need to fill it? 1. This is why they get along so well. Okay? Sodium has what chlorine needs. Chlorine has what sodium needs. Okay? So, they react with each other, they form an ionic compound, sodium chloride, table salt. Once that bond has formed, this is going to sound awful, so like don't make any sociological kind of parallels with this, but they both got what they needed. There's no need for them to stay together anymore. I know it sounds from a sociological perspective terrible, okay? But from a chemical perspective, they now have their outer shell full of electrons, which is the desire of all atoms. Okay, we're personifying a bit here, but that's kind of it. Okay, so they'll split very easily. In fact, if you put an ionic compound in water and it dissolves, it essentially splits into the charged particles. Okay, positively charged sodium atoms or ions and negatively charged chlorine ions. Okay, chlorine would be -1 because it picked up an extra electron and now has one more electron than it has protons. Sodium will be positively charged because it's lost an electron and now has one less electron than it has protons. Okay, and so now that solution has positively charged sodium ions, negatively charged chlorine ions floating around in it. Okay, which is also why ionic compounds will conduct electricity when they are dissolved in water. Okay, believe it or not, distilled water actually does not conduct electricity. It's the ions dissolved in water that actually cause it to do so. Okay? All right, does that sort of make sense? Okay, so an ionic bond is very weak and it's caused by the transfer or trading of electrons. That's all you need to know in grade 10 about the nature of ionic bonding. Okay. All right, so when we get a compound like that, okay, we have to name it and we have to be able to write a formula for it. Okay, the naming for ionic compounds is very easy. Name the metal first, name the nonmetal second, and change the ending of it to, and didn't call it sodium chlorine, I called it sodium chloride. Okay, just change the ending to ide. It's pretty simple. Okay, for normal simple binary ionic compounds, that's the rule. Okay, we just name the name of the metal and the name of the nonmetal, and we change the ending of the nonmetal to ide. Okay, very, very simple. Okay, so we could have magnesium oxide, sodium fluoride, aluminum sulfide, okay, something like that. Okay. Questions there? Does that sound familiar? Okay. Now, other things to be aware of. A chemical name is not a proper name. Okay, it's not like John Doe, okay, or something like that. It's not a proper name, thus it's not capitalized. Okay, people have a real habit of capitalizing the names of chemical compounds. They don't need to be capitalized unless you're starting a sentence with it. Okay, then grammatically you have to. Okay, but otherwise they're not a proper name, they're a designation, and as a result they're not capitalized. Okay? Alright, so if I put aluminum and chlorine together, okay, I would get aluminum chloride. Now, what are these numbers? What's the 3 and the 2 tell me?
How many of those atoms are?
Right, tells me that there's 1 aluminum atom and 3 chlorine atoms in aluminum chloride. Okay? How come they don't just go together 1 to 1? Sodium and chlorine went together 1 to 1. Why don't aluminum and chlorine go together 1 to 1? Okay. Well, if you look at your periodic table, okay, you can see right here in the top right corner of sodium's box, there's a +1. That's sodium's charge. It means it has 1 electron in its outer shell that it wants to get rid of. Aluminum, on the other hand, is +3. That means it's got 3 electrons in its outer shell it wants to get rid of. So, if aluminum wants to react with chlorine and form a compound, it doesn't need 1 chlorine, it needs 3 of them, because each chlorine can only take 1 electron. Okay, then their outer shell is full. Right? So aluminum needs 3 chlorines in order to give away all of its electrons. Does that sort of make sense? You guys learned the drop and swap last year for ionic compounds? Okay, that's why you do that. It accounts for the charges, okay, and the kind of needs of the elements that are involved. Okay. All right, let's see how we do with a couple of practice ones here. Okay. See if you can write down for me the names of the first 4 on that list. All right, so first one we already did, so that was kind of a giveaway. right? But if we're following the rules here, I name the metal first. Na stands for sodium. Okay, and Cl stands for chlorine. So that'll be sodium chloride. Okay, everybody all right with that? Okay, for number 2, what does K stand for? Potassium. Okay, and F stands for chlorine, so this will be potassium fluoride. Okay, and then for number 3, okay, we start out with hydrogen, okay, and it's with iodine, so this will be hydrogen iodide. Okay, now weird thing about hydrogen. Hydrogen can actually act as both a metal, whoops, I was thinking of it already, as a metal and a non-metal. So if it's listed first, it's behaving as the metal. So I'd write it as hydrogen, okay, and then iodide. But if it was second, it could be behaving as a non-metal. Okay, so if you see hydrogen listed first, it's a metal, that's an ionic compound. If you see hydrogen in a compound and it's anything other than first, it's behaving as a non-metal, and that's likely an ionic compound, or sorry, a molecular compound. Okay, so just something to watch out for. Okay, and for number 4, Ca stands for calcium, Br stands for bromine. Okay, so this will be calcium bromide. Does the 2 matter? Not for the name, no. Okay, we don't use prefixes in ionic compounds. Okay? The reason we don't use prefixes in ionic compounds is that is the only way that calcium and bromine can go together. Okay? Calcium is a 2+ charge, which means it needs 2 electrons to, or it needs to get rid of 2 electrons to be happy. So it's going to always need 2 bromines because bromines are a -1. All right, everybody follow me there? That's that whole drop and swap thing again. Okay. All right, questions on the first 4? Okay. Try those ones. Give you a few minutes and we'll go through them together. Let's have a look at number 5. How many people are done, let's say, up to 10? Okay, perfect. All right, so number 5, we've got aluminum and we've got astatine, or astatine, which will change to astatide, okay, because that's what we have to do for an ionic compound. So we'll have aluminum astatide, okay, and you will see, okay, that I'm writing that and pronouncing it the old way, the North American way. You'll notice on your periodic table that aluminum is not spelled the way I've spelled it, okay? It was changed to aluminium, okay? Which I think just sounds like all prim and proper, but I just can't bring myself to say it that way, okay? Like if you hear someone like with a really proper British accent say it, it sounds wonderful, but when I say it, it just sounds silly, okay? So I just say aluminum, okay? Because I don't drink pop from an aluminium can. I don't drive an all aluminium truck. It just doesn't sound right when I say it, so it's okay to say it or spell it either way. You're not going to get it marked wrong, okay? If you write it this way or the way that's on the periodic table, either way is fine, okay? All right, number 6, okay, we've got cesium and we've got sulfur, so this is going to be cesium sulfide. Okay. All right, what would we call number 7?
Sodium oxide.
Sodium oxide. Okay, and again, the little numbers don't change the name because we don't put prefixes in the names of ionic compounds. All right, what would 8 be? Yeah, barium selenide, or it could also be selenamide. It's another one of those ones that can be said either way. Okay. Okay, number 9.
Sodium chloride.
Okay. Okay, and number 10, we'll have lithium with fluorine, so this will be lithium fluoride. So hopefully this is familiar from last year, that's a U, okay? That's what you were like.
Because selenide can be 2 ways, you said?
Yes,
And
it can be
salt-
selenide or it can be selenamide.
Can sulfide also end up being sulfuride?
No,
No.
no, that one has to be changed to just sulfide. Don't ask me why I didn't make this, I just found it. Okay, what do we got left here? We got, okay, try those last 4. And then I'm gonna teach you something new with some special types of ionic compounds. Alright, so, for number 11, Rb is rubidium, S is sulfur, so this would be rubidium sulfide. Okay, Sr is strontium. So again, the metal's name is unchanged, and then it's with iodine, so we change the ending of that to ide, iodide. Okay, for number 13, Ca stands for calcium, so we write the metal unchanged, it's with oxygen, oxide. Okay, and for 14, Mg stands for magnesium, metal unchanged, and it's with selenide, so magnesium selenide, sorry, with selenium, so it's magnesium selenide. Okay, questions on that? All right. Let's say I've got these 2 compounds. What would I call those? Copper oxide. Are they the same? Absolutely not. Would they have different chemical and physical properties? Yes. Then how can they have the same name? Same elements, yes. But here's the problem we might run into. Okay, and I'm not saying that this is true because it's totally not, but let's say that I'm reading this paper on nutrition and vitamin supplements or something like that, and it's saying, you know, like, if you want to have healthier teeth, you need to have a little more cupric oxide in your blood, so you need to take supplements of this, okay? Well, if they just say copper oxide, how do I know which one of these to take? The answer is I don't. Let's make this even worse. This one's really good for your teeth. That one's acutely poisonous. I have a problem now. Okay, I don't know which one to take. They have the same name. Okay, this could be very, very bad. Both of these compounds can exist. Okay, because copper has more than one possible charge. Okay, it's what we call a multivalent metal. Okay, there are a number of metals on the periodic table that fit into this category. Okay, you can see here, there's a whole bunch that have more than one charge listed beside them. Okay, that means that their outer shell of electrons or their outer electron arrangement can vary. Okay, and so they may have more electrons in that outer shell or be willing to give more up in a reaction than other times. There's obviously a more common form. Whatever charge is most common is the first one listed. Okay, so the most common charge for copper is 2+. Okay, most copper is 2+. A small amount of it is 1+. Okay, but that still means that both of those compounds could exist. So I can't give them the same name. Okay, it would be like what happened to me about 8 years ago. I had 2 Chase William Andersons in my class. Those 2 kids could not have been more different. But they had the same first, middle, and last name, I kid you not. Okay? I to this day hope that I did their marks accurately, because I just had to have them write 1 and 2 on their tests so that I knew which one was which. Okay? If they forgot, well, I don't know what would happen. Okay? So, these can't have the same name. So when we have multivalent metals, we have to add something to the name to tell people this is the copper that has this charge, and this is the copper that has this charge. Okay? Now, first thing that means is I have to figure out which charge. this copper has. Okay? So, you guys learned about the drop and swap last year, right? You learned about how to write the charges at the top and then switch them. Okay, so the charge on oxygen is always -2. That's not listed on your periodic table for this reason. Everything that's a non-metal in group 16 has a charge of -2. Everything in group 17 that's a non-metal is a -1. Now, you're going and adding that to your periodic table. I need to caution you about this. This is something you need to memorize. You're not going to get your periodic table on the unit or final exam. Okay? I give you a fresh one. This is information you need to know. Okay? Everything in 17, -1. Everything in 16, -2. Okay? Think about it. 18's full. So -1, -2, -3. Okay? Those are the only ones you have to remember. These ones never bother doing anything, so you don't need to worry about it. Okay? So, since oxygen is always a -2, what's the charge on copper? Knowing that this compound has to come out to an overall charge of 0. Okay, if I put a +2 here and I've got 2 coppers, how many positive charges is that? That's 4. Okay, so that doesn't balance out then. So this must be the copper with the +1 charge. Okay, so I've always got to make sure a compound, an ionic compound, ends up with a net charge of 0. I got 2 negatives, I got 2 positives. So that works. That's why we do the drop and swap. Okay, what about this one? Oxygen's always a -2. Thankfully, non-metals don't have more than 1 charge. Okay, so what charge does that copper have? +2. Yeah. This is only one of it, right? There's only 1 copper here, so now it's got to have a charge of +2 to cancel out the -2, give me an overall charge of 0. Okay. So once I figure out the charge, then I can write the name. This is the copper with the 1+ charge, so I would call this stuff copper 1 oxide. This stuff I would call copper 2 oxide. So you're going to need to know your Roman numerals up to, let's say, 7. All right. So, you know, if you've watched Star Wars, okay, or Rocky, or anything that's got a lot of sequels, okay, and they're like in different episodes, and it's like Rocky 2, Rocky 3, okay, we use Roman numerals for that, okay, so, just so you know, all right, we'll just put the Roman numerals under here. So, 1, 2, 3, and this is where it changes. 4, because it's 1 less or 1 before 5. Part of the reason the Roman Empire fell, probably. Okay? It takes forever to figure out what the number is. If you ever watched the Super Bowl, they use Roman numerals for the Super Bowl. I can't even figure out what number it is anymore. When I just see it, I don't hear it. It's huge. Okay? So, those are your Roman numerals. Those would be put into your names for any ionic compound that has more than 1 charge. So you only need to use it if the metal has more than 1 charge. I wouldn't put that in sodium chloride or magnesium sulfide. Those only have 1 possible charge. I don't need a Roman numeral for those. I only need it if the metal has more than 1 possible charge. Okay? All right, so that's what we just talked about there. Okay, this is the Fe or the iron with 2 with a +2 charge. It can be a +2 or a +3. Okay, when those two go together, I get FeO, and I would have to write that as iron, Roman numeral 2, oxide, so that I don't confuse it with that stuff. Okay. What's the charge on this iron?
3.
Yeah, it's 3. Okay, now, here's the thing I caution you against. Don't just reverse the drop and swap. It's not always going to work. It'll only work about 2/3 of the time. Okay, the way that always works is to do this. Oxygen is always a -2. Always look to your non-metal. Okay, because they'll only have one possible charge. -2 times 3 means I have a total of 6 negative charges. How many positive charges do I need?
6.
Right. Okay, so if I need to get 6 positive charges from 2 iron atoms, 6 divided by 2 is 3. This is the iron with the +3 charge. So you gotta do a tiny bit of math. Yeah, you have to do a little bit of multiplication and division. Okay, nothing too taxing. So this stuff would be iron 3. Oxide. Okay. Everybody all right with that? It'll take a little bit of practice, but it's nothing terribly difficult. All right, we already did number 1, so try 2, 3, and 4. Okay, I'll just write the answer in for number 1 here. Okay, give you a few minutes on those ones. Okay, let's walk through these ones and I'll do it exactly the way that I showed you before here. All right, so I've got CO, which stands for cobalt, so I'm just going to write cobalt. Okay, and I've got sulfur, it's an ionic compound, so I'm going to write that as sulfide and just leave room for the Roman numeral because cobalt can be at 2 or 3, right? Okay, so now I've got to figure out, is this the cobalt that's the 2 or the cobalt that's the 3? And the way I do that is I use the charge of the non-metal to help me. Okay, sulfur, according to my periodic table, is in group 16. Everything there has a -2 charge, right? This compound has to have an overall charge of 0, and I only have 1 cobalt to get 2 positives from, so that cobalt must have a +2 charge. That's the only way I'll get 0, right? Okay, so this is a +2 because there's only 1 cobalt. +2 and -2 equals 0. Cobalt to sulfur. All right, number 3, Mn. Okay, Mn stands for manganese. Okay, and Cl stands for chlorine, which I will change to chloride. All right. Manganese can be a 2 or a 4, I believe. Okay. So I need again to look to my non-metal to help me out. Chlorine is in group 17. Everything in group 17 has a charge of -1. Okay, how many chlorines are there? 4. Each chlorine has a charge of -1. That means I have 4 negative charges in total. That means I need to get 4 positive charges. And I only have 1 manganese to get it from, so the charge on manganese must be 4. So, IV. Okay, everybody following my reasoning here? Okay. And for this one here, okay, I've got copper, which can be a 1 or a 2, with sulfur, which is always, since it's in group 16, -2. Since there's only 1 copper, the charge on copper must be +2. Okay, so there you can see that like reversing the drop and swap doesn't always work, right? If I don't have any numbers down there, I assume everything is 1 and that's not right. Okay, it can also be if I've reduced down, but I could also get the wrong numbers by reversing the drop and swap. So if you do it this way each time, you'll always get it right. All right, try those 4. All right, let's have a quick look at these ones here. So for number 5, SN stands for tin. Okay, and TE stands for tellurium, so this will be tin something telluride. All right, I need to figure out which Roman numeral to put on tin. I think it'd be a 2 or a 4. Okay, tellurium is in group 16. Always has a charge of -2. Okay, so how many negative charges do I have?
-4.
4. Okay, so I've got 4 negatives. That means I'm going to need 4 positives. There's only one tin here. 4 divided by 1 is 4. So this is tin, Roman numeral 4, telluride. Okay. Number 6, Hg stands for mercury. Okay, and At is astatine. So we'll have mercury something astatide. Astatide is in group 17, which means it always has a charge of -1. So I've got 2 negative charges. That means I've got to get 2 positive charges from a single mercury. Therefore, the charge on mercury is +2. So mercury 2 astatide. Everybody all right with that? Okay. And then for number 7, we've got polonium. Whoop. Not polonium. Polonium. And it's with iodine, so iodide. Okay. Iodine's in group 17, so it's a -1. There's 4 of them, so polonium must have a charge of 4. Okay, and lastly, we've got antimony with sulfur, so antimony something sulfide. I think antimony can be a 3 or a 5. Okay, so sulfur is always a -2. It's in group 16. -2 times 3 is -6. So that means I got to get 6 positive charges from 2 antimonies. 6 divided by 2 is 3. 1, 2, 3. All right. Tomorrow, we'll get a quiz on the structure of the atom. Okay, like I said, that'll post today on Google Classroom at 3:20. Okay, it's already set to do so, so make sure you check it today at 3:20 for those questions. And the answers are basically the stuff you did, okay, on those 12 questions. All right, good work today, guys.